Hello friends, in the previous lecture we learned that a process is said to be reversible if both the system and the surroundings can be restored to their original conditions and any other process is irreversible. The effects such as friction, non-quasi-equilibrium expansion or compression and heat transfer through a finite temperature difference render a process irreversible and are called irreversibilities. And finally, we discussed that the Carnot cycle is a reversible cycle that is composed of 4 reversible processes, 2 isothermal and 2 adiabatic. In today's lecture, we shall be talking about Carnot principles, thermodynamic temperature scale and the Carnot heat engine. The Carnot principles. The second law of thermodynamics puts limits on the operation of cyclic devices as expressed by the Kelvin-Planck and Clausius statements. A heat engine cannot operate by exchanging heat with a single reservoir, and a refrigerator cannot operate without a net energy input from an external source. We can draw valuable conclusions from these statements. 2 conclusions pertain to the thermal efficiency of reversible and irreversible, that is actual heat engines, and they are known as the Carnot principles, expressed as the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same 2 reservoirs. The efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. The 2 statements can be proved by demonstrating that the violation of either statement results in the violation of the second law of thermodynamics. To prove the first statement, consider 2 heat engines operating between the same reservoirs. One engine is reversible and the other is irreversible. Now each engine is supplied with the same amount of heat QH. The amount of work produced by the reversible heat engine is W reversible and the amount produced by the irreversible one is W irreversible. In violation of the first Carnot principle, we assume that the irreversible heat engine is more efficient than the reversible one and thus delivers more work than the reversible one. Now let the reversible heat engine be reversed and operate a refrigerator. This refrigerator will receive a work input of W reversible and reject heat to the high temperature reservoir. Since the refrigerator is rejecting heat in the amount of QH to the high temperature reservoir and the irreversible heat engine is receiving the same amount of heat from the reservoir, the net heat exchange from this reservoir is 0. Thus, it could be eliminated by having the refrigerator discharge QH directly into the irreversible heat engine. Now consider the refrigerator and the irreversible engine together. We have an engine that produces a net work in the amount of W irreversible minus W reversible while exchanging heat with a single reservoir, a violation of the Kelvin-Planck statement of the second law. Therefore, our initial assumption that the irreversible heat engine is more efficient than the reversible one is incorrect. Then we conclude that no heat engine can be more efficient than a reversible heat engine operating between the same reservoirs. The second Carnot principle can also be proved in a similar manner. This time, let us replace the irreversible engine by another reversible engine that is more efficient and thus delivers more work than the first reversible engine. By following through the same reasoning, we end up having an engine that produces a net amount of work while exchanging heat with a single reservoir, which is a violation of the second law. Therefore, we conclude that no reversible heat engine can be more efficient than a reversible one operating between the same two reservoirs, regardless of how the cycle is completed or the kind of working fluid used. The Carnot heat engine. The hypothetical heat engine that operates on the reversible Carnot cycle is called the Carnot heat engine. The thermal efficiency of any heat engine, reversible or irreversible, is given by this equation as eta Th is equal to 1 minus QL upon QH. Here QH is heat transferred to the heat engine from a high temperature reservoir at Th. QL is the heat rejected to a low temperature reservoir at TL. For reversible heat engines, the heat transfer ratio in the above relation can be replaced by the ratio of the absolute temperatures of the two reservoirs as given by thermodynamic temperature scale equation as QH upon QL reversible is equal to TH upon TL. Then the efficiency of a Carnot engine or any reversible heat engine becomes eta Th reversible is equal to 1 minus TL upon Th. This relation is often referred to as the Carnot efficiency, since the Carnot heat engine is the best known reversible engine. This is the highest efficiency a heat engine operating between two thermal energy reservoirs at temperature TL and Th can have. All irreversible, that is actual, heat engines operating between these two temperature limits have lower efficiencies. An actual heat engine cannot reach this maximum theoretical efficiency value because it is impossible to completely eliminate all the irreversibilities associated with the actual cycle. Note that TL and Th in the efficiency of a Carnot engine equation are absolute temperatures. Using degree centigrade or degree Fahrenheit for temperatures in this relation gives results grossly in error. The thermal efficiencies of actual and reversible heat engines operating between the same temperature limits are compared here. Eta Th is less than eta Th reversible for irreversible heat engine. Eta Th is equal to eta Th reversible for reversible heat engine and eta Th is greater than eta Th reversible for impossible heat engine. Most work producing devices, that is heat engines, in operation today have efficiencies under 40%, which appears low relative to 100%. However, when the performance of actual heat engine is assessed, the efficiencies should not be compared to 100%. Instead, they should be compared to the efficiency of a reversible heat engine operating between the same temperature limits, because this is true theoretical upper limit for the efficiency, not 100%. It is obvious from the efficiency equation that the efficiency of a Carnot heat engine increases as Th is increased or as TL is decreased. This is to be expected since as TL decreases, so does the amount of heat rejected, and as TL approaches 0, the Carnot efficiency approaches unity. This is also true for actual heat engines. The thermal efficiency of actual heat engines can be maximized by supplying heat to the engine at the highest possible temperature and rejecting heat from the engine at the lowest possible temperature. Let us solve an example here. A Carnot heat engine, as shown here, receives 500 kilojoules of heat per cycle from a high temperature source at 652 degrees centigrade and rejects heat at a low temperature sink at 30 degrees centigrade. We are to determine the thermal efficiency of this Carnot engine and the amount of heat rejected to the sink per cycle. The Carnot heat engine shown here is a reversible heat engine, and so its efficiency can be determined by the efficiency equation as eta THC is equal to eta TH reversible, which is equal to 1 minus TL upon TH. Substituting the values of TL and TH, we get eta TH reversible equal to 0.672. That is, this Carnot heat engine converts 67.2% of the heat it receives to work. The amount of heat rejected by this reversible heat engine is easily determined by this equation, where QL reversible is equal to TL upon TH into QH reversible. So, substituting the values, we get QL reversible equal to 164 kilojoules. Note that this Carnot heat engine rejects to a low temperature sink 164 kilojoule of the 500 kilojoule of heat it receives during each cycle. The quality of energy. The Carnot heat engine in example just discussed receives heat from a source at 925 Kelvin and converts 67.2% of it to work while rejecting the rest, that is 32.8%, to a sink at 303 Kelvin. Now let us examine how the thermal efficiency varies with the source temperature when the sink temperature is held constant. The thermal efficiency of a Carnot heat engine that rejects heat to a sink at 303 Kelvin is evaluated at various source temperatures and is listed here. Clearly, the thermal efficiency decreases as the source temperature is lowered. When heat is supplied to the heat engine at 500 instead of 925 Kelvin, for example, the thermal efficiency drops from 67.2 to 39.4%. That is, the fraction of heat that can be converted to work drops to 39.4% when the temperature of the source drops to 500 Kelvin. When the source temperature is 350 Kelvin, this fraction becomes a mere 13.4%. These efficiency values show that energy has quality as well as quantity. This is clear from the thermal efficiency values that more of the high temperature thermal energy can be converted to work. Therefore, the higher the temperature, the higher the quality of energy. Large quantities of solar energy, for example, can be stored in large bodies of water called solar ponds at about 350 Kelvin. This stored energy can be supplied to a heat engine to produce work such as electricity. However, the efficiency of solar pond power plants is very low, under 5%, because of the low quality of the energy stored in the source, and the construction and maintenance costs are relatively high. Therefore, they are not competitive even though the energy supply for such plants is free. The temperature and thus the quality of the solar energy stored could be raised by utilizing concentrating collectors, but the equipment cost in that case becomes very high. The Carnot refrigerator and heat pump. A refrigerator or a heat pump that operates on the reversed Carnot cycle is called a Carnot refrigerator or a Carnot heat pump. The coefficient of performance of any refrigerator or heat pump, reversible or irreversible, is given by these equations. COPR is equal to 1 upon QH divided by QL minus 1 and COPHP is equal to 1 upon 1 minus QL divided by QH. Here QL is the amount of heat absorbed from the low temperature medium and QH is the amount of heat rejected to the high temperature medium. The coefficient of performance of all reversible refrigerators or heat pumps can be determined by replacing the heat transfer ratios by the ratios of the absolute temperatures of the high and low temperature reservoirs. Then the coefficient of performance relations for reversible refrigerators and heat pumps become COPR reversible is equal to 1 upon TH divided by TL minus 1 and COPHP reversible is equal to 1 upon 1 minus TL divided by TH. These are the highest coefficients of performance that a refrigerator or a heat pump operating between the temperature limits of TL and TH can have. All actual refrigerators or heat pumps operating between these temperatures have lower coefficients of performance. The coefficients of performance of actual and reversible refrigerators operating between the same temperature limits can be compared as COPR is less than COPR reversible for irreversible refrigerator. COPR is equal to COPR reversible for reversible refrigerator and COPR is greater than COPR reversible for impossible refrigerator. A similar relation can be obtained for heat pumps by replacing all COPRs by COPHP. The COP of a reversible refrigerator or heat pump is the maximum theoretical value for the specified temperature limits. Actual refrigerators or heat pumps may approach these values as their designs are improved, but they can never reach them. As a final note, the COPs of both the refrigerators and the heat pumps decrease as TL decreases. That is, it requires more work to absorb heat from lower temperature media. As the temperature of the refrigerated space approaches 0, the amount of work required to produce a final amount of refrigeration approaches infinity and COPR approaches 0. Example. Here we discuss and find out whether a claim made by a refrigerator manufacturer is reasonable or not. The refrigerator manufacturer claims that his refrigerator maintains the refrigerated space at 35° Fahrenheit while operating in a room where the temperature is 75° Fahrenheit and that has a coefficient of performance of 13.5. An extraordinary claim made for the performance of the refrigerator can be evaluated by comparing it with the reversible refrigerator operating between the same temperature limits using this equation as COPR maximum is equal to COPR reversible and is equal to 1 upon TH divided by TL minus 1. Substituting the values in this equation, we get coefficient of performance equal to 12.4. This is the highest coefficient of performance a refrigerator can have when absorbing heat from a cool medium at 35 °F and rejecting it to a warmer medium at 75 °F. Since the coefficient of performance claimed by the inventor is above the maximum value, the claim is false. So friends, here we come to the end of our discussion and therefore we sum up. The Carnot principle states that the thermal efficiencies of all reversible heat engines operating between the same two reservoirs are the same. No heat engine is more efficient than a reversible one operating between the same two reservoirs. A heat engine that operates on the reversible Carnot cycle is called a Carnot heat engine. So that is it for today. In the next lecture, we shall be discussing entropy. Thank you very much.